Cool. So no? Yes, sir. Okay, great. So it's my great pleasure to introduce Josh Wang. He's going to tell us about the homology, SUN representations, and the trefoil.
Great. Yeah, thank you very much. And it's great to be here. So, right. So the plan of the talk is that I'm going to first tell you about a nice coincidence between the Cohonophomology of certain simple knots and links with a certain space of SU2 representations of the fundamental group of the complement. And then I'll generalize that coincidence to a generalization of Cohonophomology called SLN homology. And we'll be looking at SUN representations instead of SU2. And then finally, we'll turn to a even further generalization called colored SLN homology. Okay, so we're given an oriented link inside of the three sphere, and then we want to look at the complement of that link, look at its fundamental group, and then look at all homomorphisms from the fundamental group into SU2. And I want to look at only the representations for which every meridian is sent to a traceless matrix. Then I just take that, it's a space. I'm not going to quotient out by SU2. I'm just taking literally the set of these homomorphisms. And if you've never worked with this space before, let me tell you a very concrete way to think about it. So if you have a diagram for your link, then you have a working representation of the fundamental group. And every arc of your diagram corresponds to a meridional generator. And each meridian, each of those meridional generators needs to be sent to a traceless matrix. And the space of traceless matrices inside of SU2 forms a two-sphere. So for every arc of your diagram, you want to choose a point on the two-sphere. So if you have an arc A, you're going to choose a point lambda A. And for every crossing that you see in the diagram, there's three arcs locally in that crossing, and each of those arcs has a point on the sphere. And what we require is that if you look at the point corresponding to the overstrand, then 180-degree rotation about the axis that goes through that point should swap the 2 points corresponding to the two overstrands. And the representation space, the space of representations, is just the set of all such configurations of points. So one representation is a point on the two-sphere for every arc that satisfies this constraint for each crossing. So here's an example. You take this diagram of the Hopf link, then there's two arcs, A and B. So we're looking for a pair of points on the two-sphere. And the crossings, you can check that what they tell you is that if you rotate about one of them, it has to fix the other point. So the only possibilities are that the 2 points are at the same location, or they're antipolar. And so the representation space consists of two components, and each component is a S2. For this diagram of the trefoil, there's three arcs. So we're looking for 3 points on the sphere. And each of the crossings, what they tell you is that rotation about one of them has to swap the other two. And so the only possibilities are that one possibility is they're all at the same location. But it turns out the only other possibility is that they're equidistant on a great circle. And so the representation space consists of an S2, and then all of the points that are equidistant on a great circle, and you can check that you can identify it with SO3. Okay, so that's what this representation space is. You can think of it fairly concretely. And the observation I wanted to tell you about is that if you look at the 2n torus knots and links, and you look at this representation space, and then take the cohomology, it coincides with the Khovanov homology of the link. And they coincide as abelian groups. So over Z, they also coincide for any coefficient ring. And you can say something about gradings, but it's a little bit complicated, so I'm going to ignore gradings for this talk. Right. And so let me give you a few examples. So for the unknot, the representation space, it's just a free choice of one point on the sphere. So the representation space is the two sphere. Cohonophomology is two copies of Z, matches the cohomology of the two sphere. The two component unlink, they match up. The hop link also matches up. If you're very familiar with Cohonophomology, you know that these two Z4s are different looking Z4s, and it's kind of reflected in the representation spaces. We saw this trefoil example, and then just two more for fun. These representation spaces. It turns out that for all the 2n torus knots and links, the representation spaces are all just built out of S2s and SO3s. Okay, now I want to slightly enhance this coincidence. So from our very explicit understanding of this representation space, suppose you pick an actual, like one of the arcs in your diagram. You pick one of your arcs, and then define a map which goes from the representation space down to S2, which is just tell me the location of the point corresponding to that arc. So that's a map from the representation space to S2, and it turns out that's a fiber bundle. You can look at the fiber over your favorite point in the two sphere, and we'll call that R2 bar. And I'll think of it as a quote unquote reduced space of SU2 representations. And then notice that from this topological map, from the representation space to S2, we get an induced map on cohomology going the other way, which makes the cohomology of the representation space into a module of the cohomology of the two sphere, in which you can think of it as the adjoint exponent square. So if you're familiar with Cohonophomology, these two pieces of data might start to sound familiar. And indeed, if you look again at these 2n torus knots and links, there's something called reduced Cohonophomology, which depends on a choice of base point, which you can think of as distinguishing an arc. And the reduced Cohonophomology matches the cohomology of this reduced representation space. And furthermore, that choice of base point induces a base point action on Cohonophomology, which makes it into a module of the Z adjoint epsilon x squared, and it matches up with this Z adjoint epsilon x squared module structure on the cohomology of the representation space. It's pretty nice. Like a lot of the algebraic features that you see for Cohonophomology. You just look at these 2n torus knots and links. You can see a topological version of it for the representation spaces. Okay, and also if you just look at two bridge knots and links, rational knots and links, then this observation still holds. It coincides for all rational knots and links. But there are counterexamples, so it's not true for all knots and links. There are even alternating examples. Okay, so to tell you a little bit more about the picture in which this coincidence sits. So apparently, Kronheimer and Mrowka noticed this observation, and it inspired them to relate Cohonophomology to a version of instanton homology using SU2. So they defined an SU2 instanton homology that's called I sharp, and they defined a spectral sequence from Cohonophomology to I sharp. And I won't say too much about it, but I sharp, it's some kind of Morse homology for a function that's called the transimus functional. So it's some kind of Morse homology for a transimus functional for a function. And the way that this representation variety shows up is that it's the set of critical points of this function. So the function itself is not Morse because its critical set is a manifold. It's not a select collection of discrete points. However, if that Chern-Simons functional happens to be Morse bond, then you would expect the spectral sequence from the cohomology of the critical set to the actual Morse homology. So sometimes, but not always, there's a spectral sequence which goes from the cohomology of this representation party that we've been talking about to the instanton homology. And so you can think of the coincidence on the previous page as the statement that for rational links, both of these spectral sequences exist and also just immediately degenerate. And so all three of these groups are the same. Are there any questions? Okay. So now I want to turn to a generalization. So Cohonophomology is a categorification of the Jones polynomial. And it turns out that the Jones polynomial is one of a family of link polynomials called the SLN link polynomials. And they satisfy a scaling relation, and in particular, they're a spectralization of the Huntley PT polynomial. Right, and the SL2 link polynomial is the Jones polynomial. And SLN link homology, it's a categorification of the SLN polynomial. So it's just like Cohonophomology, it's defined as the homology of a chain complex associated to a diagram. It's a bigraded invariant. And the SL2 link homology is isomorphic to Cohonophomology. So it's just a family of further generalizations of Cohonophomology. And it was first defined by Khovanov and Rosansky over Q, and that's why it's denoted AR sub n. And it was not until quite recently that there was a version of it defined over Z that really makes it look like how Cohonophomology is defined. So I implicitly work with the versions defined by these authors. And the definition is really nicely just a straightforward generalization of, well, it's maybe not so straightforward, but it's really analogous to how Cohonophomology is defined. Okay, and I want to say a little bit about how it's defined. And to do that, first tell you about something at the classical sort of level about the polynomials. And it's that this polynomial, which is defined for links, you can actually define it for certain trivalent graphs in the plane. And I'll say more about what those trivalent graphs are. But there's some collection of trivalent graphs for which this polynomial is defined. And with respect to that new extension of the polynomial, there are these two other scaling relations. So the original scaling relation is sort of for links, but here we've now got these trivalent graphs shown. So for recrossing, there's two possible choices of resolution. One is the oriented resolution. The other one is almost the unoriented resolution, except you've added an extra edge, making it a trivalent graph. And the edges of these trivalent graphs, they are equipped with an orientation, they're oriented trivalent graphs, and they're also equipped with a weight. Each edge is equipped with a label or a weight. And they satisfy the flow condition, which is to say that the weights of incoming edges to every vertex must sum up to the weights of the outgoing edges. So here I'm thinking of these unlabeled edges as labeled 1. So you've got 2 that flow in to an edge labeled 2, and this edge labeled 2 splits into edges labeled 1. So these kinds of graphs, trivalent graphs oriented with weights, those are what are called MOI graphs. And PN extends to them. Okay, and it's this relation that you categorify to define the Khovanov-Rosansky homology. So, right, just like Khovanov homology, SLN homology, it's the homology of a chain complex, and the chain complex is obtained from a diagram by same cube of resolutions. So I'll first show a picture and then explain it a little more. So the complex that's associated to a crossing, well, the complex associated to a diagram, what you do is you look at all the crossings, you choose a resolution for each of the crossings to get a complete resolution, just as in Cohonophomology. Those are the vertices of the cube. And then on the edges of the cube, there are these quote unquote cobordisms that go between those tribanded graphs. They look locally like these pictures. And then associated to every MOY graph is a state space that I'll call CN. And at every vertex, you've got an MOY graph and you associate to it its state space. And the state spaces have a property that if you have a cobordism between MOY graphs, those are called foams, you get a map between them. And so your chain group is the direct sum of all the state spaces over the vertices, and your differential is a signed sum of the maps induced by these elementary foams. Okay, and I'll note that this chain group, this state space of a particular resolution of a particular MOY graph, it's actually just a free abelian group. It has a grading, and its graded rank is just the polynomial. So the abstractly what the group is completely determined just by the classical thing, the polynomial. But what's interesting about them are the maps between them given by forms. Okay. Right. So that's Khovanov-Brzezinski homology. That's SLN homology. Now we're also going to look at a space of representations, but now we're going to look at SUN representations. So again, we'll look at homomorphisms from the fundamental group into SUN, and we'll also require that every meridian goes into a particular conjugacy class, and it's the conjugacy class that I'll denote by C1, and it's the class of this particular matrix. So what this matrix is it's a diagonal matrix. It's got a single -1, and then the rest are ones. And then I multiply it by a particular root of unity. This thing will actually lie inside of SUN with that root of unity there. Now, you can actually understand this space, this conjugacy class, quite explicitly. So if you take a matrix in the conjugacy class, it's a matrix, and so it has a unitary matrix. So it gives you an orthogonal decomposition of CM. One eigenspace is the eigenspace corresponding to this -1 block, and it's just a line. It's a particular line in CN. And its orthogonal complement is the eigenspace of the other block, which will be an n-1 dimensional vector subspace. So the matrix A determines a line inside of CN, like a particular one-dimensional vector subspace. And conversely, if you give me a line, like a one-dimensional vector subspace, I can define you a matrix A inside of C1 just from this formula. So you can think of this conjugacy class, you can identify it with just CPN -1. So that's how when n was 2, the space of this, yeah, so when n is 2, this space is S2, and this conjugacy class is the conjugacy class of traceless matrices.
So the traceless condition was sort of a coincidence.
Yeah, that's like maybe a red herring. Well, some people might take a different viewpoint. Like you could choose different conditions on where your meridians should go. And if you choose different places for the meridians to go, you get different spaces, and there should be sort of interesting gauge theory for those different choices. But it's this choice that will be related to SLN homology. Right. So just like before, if you've got a diagram for the link, you can think of this space fairly concretely. You just choose a point in projected space for every arc, and there's a constraint for each crossing. So here's some examples of these spaces. So the unknot, you're just free to choose where that point goes inside of CPN -1. unlink, you just have two free choices. For the hop link, there's now two components. One component is a copy of CPN -1. So that's where the two arcs go to the same line. But then there's another component, and that other component is a partial flag manifold. And my notation 1 to n denotes the space of a line in a plane inside of CN, which is equivalent to ordered tuples of lines that are orthogonal inside of CN. So this is actually how you should maybe think about it. It's the two lines corresponding to the two arcs that are actually just orthogonal. So they're either at the same spot or they have to be orthogonal. So there's two components. The trefoil has two components. Again, a CPN -1 where all 3 points go to the same spot. But then there's an interesting other component. And it turns out it's the unit tangent bundle of CPN -1. It's pretty cool. And then turns out that for the rest of the 2n torus constant links, it's just built from these three basic spaces. It's always just, you've always got one copy of projected space. You have a bunch of copies of X being the tangent bundle. And if you're a link, you have a copy of this other flag.
How do you see the unit tangent?
I think it would be, maybe we should talk about that. Yeah, but you can do it pretty. Yeah, let's just talk about it after this. Okay, so I'll note that the traceless SU2, meridian traceless SU2 representations, that space was first studied by Xiaosong Lin. And then this generalization to SUN was defined by Kronheimer and Mrowka, etc. Okay. Right. And so just like in the Khovanov picture, you'd expect actually something similar for Khovanov-Rzansky homology, for SL homology. What you'd expect is that there's some SUN instanton homology for links with a spectral sequence from Khovanov-Rzansky homology. And you expect that this instanton homology is defined as a Morse theory for a function whose critical set is this representation. So that sometimes you get a spectral sequence from the cohomology of the representation space to the instanton homology. I think this is actually a very interesting problem to try to construct this and the spectral sequence. But that's quite hard. And before doing that, one thing you could try to check is if the Khovanov-Rzansky homology matches the cohomology of this representation space. And if they do coincide, that I think gives fairly good evidence that there exists this picture. And if they don't coincide, then maybe you pick the wrong representation space.
Like for the two knots?
Yeah, for like, yeah, just for like 2n torus knots for simple knots, even just the trefoil. Now, actually, Kronheimer and Mrowka, they did define an SUN instanton, and they defined it in order. They defined it like motivated by there existing a spectral sequence from the one. But unfortunately, after they constructed their invariant, they later proved that if n is at least 3, the dimension of their invariant doesn't change when you cross interchange. So it's not really what you would expect to live here. But it is actually defined by a more small representation. Exactly. So it's
And there's nothing that has anything to do with whether there's components across the change.
no, that's also fine, I think. I guess I'm not so sure, but I think it also doesn't matter. It's different components. At the very least, for knots, it's always the same as the invariant. Yeah, but that actually looks like Lie homology. So it could be that like the currently existing SUN homology is related to like a Lie homology for so on. So it could still fit this picture. Okay. So now I want to say that indeed for the two n-torus constant links, SLN homology matches the cohomology of this representation space. And again, as abelian groups, and this further enhancement also all holds. So if you've got a base point on the diagram, there's a reduced SLN homology group and a module structure on SLN homology. It's a module over z joint x mod x to the n. And then on the representation side, you get a fiber bundle, the same as before, defining a reduced space of SUN representations and a module structure and a cohomology of the representation space. And all of these just nicely match up for two n-torus constant links. Okay. And I call this an observation because actually all of these things are simple enough that you could just calculate both sides and see that they're the same. You don't really need anything clever. You could just calculate, just calculate and see that they match. However, where I want to go, the colored SLN, you can't just compute it. It's a little bit too unwieldy to actually compute. And what I want to do now is explain a proof of this isomorphism that's a little more clever than just calculate both sides and see that it's. And then it's that kind of argument that you have to use to go to a further generalization. Okay, so first, if you've got two crossings, one on top of the other, then for every crossing, there's two different resolutions. So you'd expect that there's, in total, there's 4 different resolutions. And you have edge maps that go between them all. And there's a nice argument due to Krasner of how to simplify this complex. I won't go into the details, but I just want to give you an impression of what you could do. So somehow, this most complicated looking one actually simplifies into the direct sum of 2 other pieces. And you can figure out what all the maps are. There are base point maps in Khovanov's homology, just like in Cohonophomology. These are what all the maps are. The Z's denote the standard sort of saddle of the definition of crossing. And then you can use some well-known simplification tricks for chain complexes to simplify the complex. And what you get are just 3 terms rather than the original 4. So you can simplify it in some way. But now, if you add an arc on the left and an arc on the right to each of these pictures, you get the complex, you get a simplification of the complex associated to a hot link. And what it is you close up these, you close up this one, you get this picture. You take its state space and you have a map to the state space of this theta graph. And then this map right here, which is a difference of dot maps, difference of base point maps. Once you've closed up on the right, the dots lie on the same arc, so they're the same map. So this map is actually 0, so you see no differential here. You just get a copy of this. Okay. Now, it turns out that, I mean, this first little complex, these 2 terms, that's the definition of the complex for this process, for this diagram. And by a Reidemeister-Wang invariance, that's just the complex of a single unknot. And once you've got a complex of a single unknot, then there's no more differential in this complex. So the complex is the homology. So the Khovanov-Rzansky homology of the Hopf link is just the direct sum of the state space of the unknot and the direct sum and with the state space of the theta graph. Okay, and then I mentioned before that the state space as an abstract group, it's determined just by the polynomial invariant. Like the thing that's interesting about state spaces are the maps between them, but now we don't care about any maps between them. So you can figure out what the group is just by knowing what the polynomial is. And if you do that, then you can check that, in fact, this state space matches the cohomology of the projective space. This one matches the cohomology of this particular. Okay, And that was the representation space of the hop link. Okay, but so this argument, it's literally just calculate both sides. So I haven't really done anything clever yet, but I will for the trefoil. But before doing that, I want to mention one thing, and it's that this state space is an actual group, and this cohomology is also an actual group. And we know abstractly that they're isomorphic, but you can actually literally define an isomorphism. And you can literally identify these two groups. And you can do so in a nice way. And I want to tell you about one nice thing that you can get by choosing your isomorphism right. So over this partial flag manifold, which we want to think of as a pair of ordered lines that are orthogonal, there are two special topological line bundles over this space. So over a particular pair of lines, the fiber of the first line bundle is the first line. And over that same pair, the fiber of the other line bundle is the second line. So they're topological line bundles. And they have turn classes. And their first turn classes, in fact, form a basis for the second homology. And you can set up the isomorphism so that cut product with the first turn class of one of the bundles matches the dot map, and cut product with the other turn class matches the other dot map. Okay. So now, if we have 3 twists instead of 2, then I claim there's a similar simplification you can do. You see the same difference of dot maps as before, but now you have a different difference of dot maps. And if you close up on the left and the right, you get a simplification of the complex of the trefoil. This map in the middle, it's 0 because we're again just closing up on the right. The 2 dot maps are the same. The first 2 terms, just as before, is the complex associated to a 1 crossing unknot, which again simplifies just to the state space of an unknot. But then there's an interesting piece left over, and it goes from the state space of this theta graph to itself, and the map is this difference of dot maps. And we can identify these complexes with the cohomologies of these spaces, the cohomology of projective space, the cohomology of this flag manifold. And now it's mapping to itself by cut product with this difference of first term. Okay. And I'll remind you that the trefoil, its representation space, is a copy of this projective space, and then a copy of this unit tangent bundle. So we want to figure out how could we show that the cohomology of this unit tangent bundle of CPM maximum is computed by this short level complex. So now this is where you could just calculate it. Like we have enough of an understanding of the cohomology of partial flag manifolds that you could do it out. But let me tell you something a little better. So it turns out that this X, this unit tangent bundle, it's actually a bundle in a number of different interesting ways. And one way is that it's a bundle over this partial flag manifold in question with fiber as circle. I mean, you can think of it as if you've got a line and a unit tangent vector to that line going in that direction defines a plane, the line in that plane. Okay, but it's a circle bundle, and so it has an Euler class. And if you calculate that Euler class, it magically turns out to be this difference of first term classes. And associated to a circle bundle is a Giesen exact sequence. And the Giesen exact sequence, it looks like you map from the cohomology of this flag manifold, the guy downstairs, to itself by wedge product with the Euler class. Then the third term is the cohomology of the total space. And so you've related the cohomology of X, this unit tangent bundle, to this complex given by mapping from the cohomology of the flag manifold to itself wedge product with this difference of first term. So strictly speaking, this guy is an extension of the co-kernel by the kernel or the kernel by the co-kernel. But you can show there are no non-trivial extensions because of the cohomology of these flag manifolds are supported only in words. So this guy actually, this homology actually is the cohomology of this concept. And I think this is a cool computation because there's actually Z mod n portion in this cohomology. And we really didn't have to actually calculate it to show that. Okay. So now I want to talk about a further generalization. So there's a thing called colored SLN homology. And now it's not an invariant of an oriented link. You need a little extra data, and what you need is a number associated to every component of that link. And that number is just a number between 0 and n. When the number is 0 or n, then it's a trivial sort of invariant. So you should think of the numbers as being between 1 and -1. And ordinary SLN homology is when all the labels are 1. So this was defined first by Wu, and then in the same papers I mentioned before, defined over Z. And in case you know about this, it's also a bigraded invariant, and its decategorification is the Reshetikhin-Turayev polynomial invariant associated to the fundamental representations of SLN. Okay, so the way that it's constructed is very analogous to the way ordinary Khovanov-Brzezinski homology is constructed, but instead of a cube of resolutions, which is gotten by just 2 resolutions of every crossing, now there are more resolutions for each crossing. How many resolutions depends on the actual labels. But in the case of a crossing involving strands labeled 2, there are 3 resolutions. These are 3 particular MOY maps. And you associate them with state spaces, and there are particular simple coordinates that go between them. And you just run the same sort of construction. Right, so you get a rectangular prism of resolutions. If the strands are labeled I and J, then you again just get a row. You just get a row of these resolutions, and the length of that row is the smaller of the 2 labels plus 1. Okay, and then here's an example of what happens for stacking 2 of these. The invariant becomes extremely big very fast. So we have a 3x3 grid that comes from the labels being 2. And then the size of each of the terms, like the state spaces, how big it is, that grows with that. Okay, so that's colored SLN homology. What about SUN representations? So what we're going to do is we're still going to look for just ordinary SUN representations, homomorphisms from pi 1 into SUN. But now we're going to change the condition on meridians. So if you've got a meridian of a component of your link that's labeled K, we're going to ask that it goes into the conjugacy class, a new conjugacy class that depends on K. And what it is it's the conjugacy class of, again, a diagonal matrix, but now you have K minus 1s instead of a single minus 1. And the rest are all just 1s. And you multiply by the previous root of unity to the K power. Okay. And just as before, you can understand this conjugacy class quite explicitly. A matrix is determined just by its eigenspace corresponding to this block. And now that eigenspace will be a k-dimensional vector subspace of Cn. So you can identify this conjugacy class with the complex Grassmannian of k-planes inside the space. Okay, so I'll give you 2 examples of this representation space. So if you take the hop link labeled 2, 2, then now there's 3 components. One is, so for the hop link labeled 2, 2, you're looking for a pair of 2 planes inside of Cn. Now those two planes could be the same 2 planes, in which case you get a copy of the Grassmannian G2n. They could intersect along a line, and be orthogonal otherwise. That's the data of a line inside of a plane, inside of a free plane, inside of span. Or they could be totally orthogonal, in which case you have the data of a plane in multiple spaces. And then for the trefoil label 2, you get something. Again, there's one component, which is the Cross-Monian, and then there's 2 components, and they turn out to be homogeneous spaces for 3D. Doesn't really matter, but if you want to know what my notation means, it's very explicit which subgroups are part of it. That's right. Yeah, the label on the arcs are 2. Okay. So there are actually, like maybe you can imagine, there are very few computations of colored Khovanov-Brzezinski homology. It's known for an unknot, which is good. And for the unknot, it does actually match the cohomology of this cross module. So that's a good first step. For the hop link, if you label one of the components 1 and you label the other component anything, then this was calculated by Yonezawa before it was defined over Z. So this was calculated over Q. But I think that this computation doesn't really get at the real complexity of colored SLN homology, because the length of that complex associated to a crossing is just dependent on the smaller of the 2 labels. So if one of the labels is 1, then the top link complex is actually still just 4 terms. But there's a computation for the hop link done using physics, and for the hop link labeled any 2 labels. And that's it. Those are the only computations for colored SLN homology when at least when things are labeled, when at least one component is labeled above 1. So the conjecture, or the heuristic, the story that I've been presenting, suggesting that maybe the colored SLN homology of 2n torus constant links matches the cohomology of that space of representations. That's a pretty non-trivial claim. That's a pretty non-trivial sort of assertion. And I'm working on it. And what I do know, what I can show, is that they match for the hop link with any labels. And they also match for the trefoil label 2. And in fact, you can also get that the module structures and reduced theories agree. And I haven't written it down yet, but I'm pretty certain that I can soon get the trefoil with any label and the torus Nansen mix, 2n torus Nansen mix label 2. Okay. So let me tell you a little bit about how the hop link labeled 2, how it matches up, and then how the trefoil labeled 2 matches up. And in particular, I want to focus on where that Giessen exact triangle argument, how that sort of manifests itself. So let me just recall that for the hop link labeled 1, I explained that there's a simplification that you could do to show that its King complex simplifies to the sum of those 2 state spaces. And I claim that with some work and some new tricks, you can show that the hop link label 2, it simplifies into the direct sum of 3 state spaces for these 3 particular MOI graphs. And this is what the representation space is. It's also got 3 pieces. And I claim that you can just calculate that that the state spaces, these MOI graphs, their polynomials match the Poincare polynomials of these spaces. And so you find that the state spaces are isomorphic to the cohomologies of these spaces. But just as before, you can actually literally identify them. It's not just an abstract identification. you can actually identify them in such a way that like Turing classes of certain bundles go to non-maps on the symbol graphs. Okay, and then for the trefoil labeled 1, what we saw from before was that its complex simplified into the sum of two complexes, one with no differential, and the other one was these two terms, both the homology representation space of this flag manifold, and the map was the difference of Turing classes. For the trefoil labeled 2, this requires a lot more work, but you can show that it simplifies into the sum of 3 chain complexes. One has no differential, cohomology with us finding it. Another one kind of looks like the one we've already seen before. It's just 2 terms, they're both the same, and the map is the difference of first chain classes. But then this third complex is more troublesome. But it's all 4 terms are the same. It's the cohomology flag manifold. And the maps are again differences of Turing classes. This is a difference of first Turing classes. This is a difference of second. Okay, and the representation space consists of 3 pieces. And what you'd like is that the cohomology of each piece matches the cohomology of each of these. Now, for the first guy, you can actually run a similar argument from before. So what you hope is that this space is a circle bundle over F1, 2, 3. Calculate its Euler class. And that actually works. You can show that this computes the cohomology of the space. But now this one's more troublesome. I mean, this doesn't look like anything you've seen before. And in fact, for a while, I was worried that maybe the cohomology of this space, it actually has a spectral sequence from the cohomology of this complex. So maybe there's like an extra differential that goes from the bottom to the top. But in fact, they do match up. And the way that I show that they match up is by a theorem in algebraic topology from the 70s that's known as the collapse theorem. And it's a theorem about how to calculate the cohomology of a homogeneous space. So if you've got a lead group G and a closed Lie subgroup satisfying certain conditions, then the cohomology of that space can be calculated by a torr. The BG and BK are classified spaces. And I'll just remind you that torr is obtained by you first take a projective resolution of one of the terms, and then you tensor it with the other terms. You get a chain complex, and then you take homology. So this side is a homology, this side is also a homology complex. And the key idea in applying this to showing that the complex arising in colored Khovanov-Rosansky homology matches the cohomology of that homogeneous space is that you literally manually choose a particular projective resolution of the cohomology of BK in this scenario, so that once you tensor it with Z, you literally get the chain complex arising in Khovanov. So that then the cohomologies match up, even though you haven't calculated what the cohomologies are. So that's what I wanted to say. Thanks very much. So I'm not so certain about literally just distinguishing knots, but there's a way to extract a numerical invariant like Rasmussen's S from SLN homology. And S can be used to prove that certain things are not slice. Sorry, the SLN S can be used to prove that certain things are not slice, where ordinary S doesn't. So there is more topological information, or at least different. I mean, yeah.
Do you happen to know? So I noticed like at the beginning you don't take the quotient by compilation, but if you do in that case, you wind up with something that has like a symplectic form, possibly a Taylor form. you know.
Well, so for these knots and links, the two inverse knots and links and also the rational knots and links, if you quotient out by conjugation, you get a discrete set of points. So yeah, whatever extra structure there is would be degenerate for these knots and links.
That's like a very simple question because I forgot that what the notation down to people.
Oh, what I meant by that was a diagonal embedding.
Okay,
So
so
like U1 times the diagonal copy U1 times U minus 3. I'm looking at block matrices where I've got 3 blocks of size 1 and a block of size minus 3. And I just want that the two of those blocks are the same. Same thing with this diagonal.
no other questions, please, that's Josh again. So we'll go to there at 5. And I think the plan is that's what's best. So if you want to do there, maybe around 5:30.
Thank you. That was a great talk.
Thanks.
Thank you.